great. So let me briefly introduce Max SPONNER. Max is a PhD student at Infineon's new development center in Dresden, and his interests are in deep learning applications. So Max, please carry on.
Thank you for the kind introduction. I also want to thank the audience for their attendance. And for our project, we've looked into compilers that bring deep learning models to embedded hardware and accelerators. So at first, I want to start with a quick motivation for our project. So we basically came up with 3 questions when we wondered how to solve the software side of things if we want to develop our own AI accelerator for embedded targets. The first question was, how would we implement the software stack for our hardware? Then are there already solutions available that we could leverage? And the third question was, how much effort is required to build our own software stack for the hardware? We set ourselves 4 requirements. The first one is the ability to target domain-specific optimizations. So the toolchain should automatically perform typical deep learning optimizations. For the embedded use case, the most important is probably the quantization, where the floating point weights and intermediates are replaced by fixed point representations to reduce the computational overhead and enable deep learning on hardware without floating point capabilities. The second requirement was a change of input format compared to standard compiler toolchains. So instead of handwritten source code, we would like to operate on the newer network description, which is provided by the deep learning frameworks. And to be less dependent on a single framework, we would like to support as many of them as possible. The third goal was the automatic targeting of mass kernel libraries. So depending on the selected target, the toolchain should automatically find the best function kernels, either from a mass kernel library or by auto-tuning, which is a solution where the compiler automatically finds the most optimal schedule by profiling the target device during the compilation process. And again, the most important library for our use case would probably be ARM-CM, this library, as we are most likely going to target Cortex-M CPUs. And the last goal was ability to target heterogeneous platforms. So in that case, an accelerator specific for deep learning would support the system CPU. And these accelerators often feature a coarse-grained instruction set architecture and often require special optimizations in terms of data types or control flow procedures, which makes them hard to target with standard compiler toolchains. Now for our benchmark. So we found 6 already available deep learning compiler toolchains. The first one is Glow, which is developed by Facebook. And its main advantage compared to the other toolchains is that it does not require a runtime to be present on the target itself. So it's reusing LLVM backends for the different targets to directly generate object files from the network descriptions. And that's the main advantage here. So the next compiler is TVM, which is maintained by the Apache Foundation. It's the only solution that performs auto-tuning with its AutoTVM component, and it also has the most advanced API to target new accelerator hardware and libraries. TensorFlow Lite is one of 2 compiler toolchains by Google. This one is targeting mobile and embedded applications. So it consists of 2 parts. The first one is the converter, which is the offline compilation stage that converts the network description into an intermediate file. At this stage, no target-specific optimizations are performed, and the output is portable across all supported targets. The second stage is the runtime, which must be present on the target and unpacks the intermediate file and is able to execute the contained networks. And the target-specific optimizations here are limited to the function kernels in the runtime. There are currently 2 major versions of the runtime available. The first one is a standard runtime that focuses on mobile platforms, so Cortex-A CPUs and Mali GPUs, while the runtime for microcontrollers is more focused on Cortex-M and other microcontroller solutions. The Intel ngraph compiler and TensorFlow XLA are both not as relevant for the embedded use case, as they are more focused on x86 and data center as well as workstation use cases. And the last compiler is the Open Network compiler, which focuses directly on AI accelerators with a coarse-grained instruction set. Now for the comparison of their features and functionality. So for the embedded use case, we basically need three features. The first one is a ahead-of-time compilation mode to just offload these tasks from the embedded platform, and the quantization as well as the targeting of mask kernel libraries and auto-tuning are used to perform the to improve the performance on the low-powered platforms. Our observations here were that TensorFlow XAA and the OpenU Network compiler were unable to perform any kind of quantization, while TVM provided the only more flexible quantization solution, where the developer could select the bit width as well as the rounding behavior. However, this comes at the cost that as it's only using a global quantization solution, which drastically reduces the accuracy, whereas the other solutions are profile guided and only support a limited number of formats. Other observations were that TVM is, as previously mentioned, the only auto-tuning capable solution, but it can also target mask kernel libraries, and the only toolchain that is unable to do so is Glow, which just relies on a generalized set of function kernels across all targets that are then optimized by the LLVM backend. Now for the front-end capabilities. So as we want to support a broad selection of different deep learning frameworks, the ONNX format is the most interesting one for us. It's a kind of industry standard and maintains converters for most of the available and popular frameworks. However, the TensorFlow Lite flat buffer file format is also quite interesting. That's the output of the TensorFlow Lite converter stage. So it already contains the state-of-the-art quantization and often graph level optimizations that can be exploited by other toolchains, and that's actually done by Glow as well as TVM. For the remaining frameworks and formats, TVM also has the broadest support, as it supports all of our tested frameworks and formats, whereas the TensorFlow compiler toolchains limits the user into the TensorFlow ecosystem, and the compiler with the least amount of support is the OpenU Network compiler that only supports an older subset of the ONNX standard. Now for our actual performance benchmarks. So we've tested 3 platforms in the paper. I'm only going to introduce 2 of them here. The first one is the ARM Cortex-M55 CPU. It's our only real embedded target, as the support for embedded hardware is quite limited in the currently available deep learning toolchains. And we've chosen this target due to its novel helium vector extension. And because it's quite new, we had to use an instruction level simulator as no hardware was available at the time of testing. To get a more complete overview over the actual performance numbers, we also added an ARM Cortex A72 as an additional target, which is more of a mobile platform. And this platform also allowed a direct comparison to the standard TensorFlow framework. Now for the performance on the Cortex-M55. So the model only allowed us to measure the instruction count as well as the peak memory allocation during a single inference. And only TensorFlow Lite for microcontrollers and the OpenU Network compiler were able to target this hardware. On the right, you can see that for the instruction count, which directly translate to the inference speed, TensorFlow Lite for microcontrollers achieved a slight speed up compared to the OpenU Network compiler. However, the OpenU Network compiler is able to cut its peak memory allocation in half compared to TensorFlow Lite Micro. So as long as your network can be compiled by both toolchains, it comes down to the individual project you want to build. On the A72, we could test additional toolchains and compilers. And our key observations here were that TensorFlow Lite achieved the fastest inference time using a quantized model. And generally speaking, the quantization usually achieved a performance improvement across all toolchains with the exception of Glow. And the reason here is that Glow does not provide optimized function kernels for the quantized execution. So it needs to fall back to floating point computations, adding additional overhead. Another observation was that the auto-tuning flow of TVM was able to improve the performance with around 30 minutes of tuning time for the quantized network. However, for the floating point network, this tuning failed as no usable or targetable schedules could be found. So I tried to apply an x86 schedule to the Cortex-A platform, resulting in the worst performance out of the compiled networks. However, if you compare this result to the standard TensorFlow framework, you see that it's still a drastic performance increasement of around, with a speed up of around 16 times, while the fastest network achieved a speed up of around 280 times. Now for our own implementation, we have chosen to also build an heterogeneous platform, so our system CPU would be supported by a dedicated deep learning accelerator, and the compiler should map as many of the supported operations to the accelerator while automatically falling back to the CPU for unsupported operations. The accelerator itself also uses a coarse-grained instruction set architecture and performs the majority of its operations on 8-bit integer input data, and it's also using an exclusive on-chip buffer that needs to be managed by the compiler beforehand. And for the toolchain, we have chosen to reuse TVM, especially for its broad front-end support and also for its bring your own code generation flow, which makes it quite easy to target such platforms. For our evaluation, we've chosen two major workloads. The first one was a MNIST test network, and it was mainly used for the functional correctness testing. So our compiler was able to split the workload according to the available on-device buffer sizes, and it also targets the longer pipelines of the accelerator, which correspond to common graph patterns of the neural network graphs. Our output was equal to the standard TVM runtimes output. However, in this use case, we had some limitations in terms of performance with unnecessary memory transactions. The second test case was a fully sized mobile net v1, which is more of the upper limit of our targeted network workloads. And again, our output was equal to the standard TVM runtime. And again, we had some performance limitations, and in both cases, these performance limitations and also accuracy drops were caused by TVM's quantization flow. Now for an additional test case, we figured that our hardware is quite inflexible, so its coarse-grained instruction set limited its ability to target new layer types and operations, which come up quite regularly in the research community. And to extend our product life, we would like to use a compiler to map new layers to already existing instructions. And to test this, we actually removed the instruction for the depth-wise convolutional layers, which make up around 3% of the total operations of a mobile net inference. And the compiler instead would map these layers to the standard convolution. While this would take a penalty in utilization and latency, we would still be able to execute this layer on the accelerator hardware. But as you can see, this plan didn't work out. So on the left, you can see the compiler supported flow without the special instruction. And for some of the hardware configurations, you can see that these 3% of operations caused more than half of the total cycle spent. And compared to a native solution, this is not a valuable solution. So CPU fallback might be a better idea, especially if you use Cortex M55 with its novel vector extension. Now to our conclusion. So for the available toolchains and compilers, we were impressed by the broad selection of already available solutions, which also showed an impressive performance compared to the standard TensorFlow framework. However, most of them were not optimized or even suited for the embedded microcontroller use case. So we couldn't find an ideal solution for tinyML, and especially not in combination with a heterogeneous accelerator. For our own implementation, we were able to test or compile all of the tested networks. However, we always had some performance limitations, and the accuracy was often reduced when we used the TVM quantization flow. However, this could be bypassed by using pre-quantized networks. And another drawback was that the current solution is unable to target Cortex-M CPUs or other microcontrollers, as the bring your own code generation flow is not implemented in microTVM, and microTVM is currently still in an early development stage. However, with our last example, we have shown that this solution can already be used during the product prototyping to test real-world use cases quite fast with the available hardware. So this was a quick overview of our work. Thanks for your attention.
Thank you, Max, for the presentation. So there is one question on Evente from Adrian. Did you look at the tools from STM, such as stmcube.ai?
Not really. We focused on open source solutions that I'm not aware of STM's solution, actually.
Okay.
Max, I have one question. So in one of your slides, actually it was, I guess, the first slide that you showed about support for heterogeneous platform, and you mentioned TPU. Have you, right? Have you tried that?
No, we focused on our own accelerator design or simulator of accelerator designs. So the edge TPU can only be targeted by TensorFlow Lite as far as I'm aware.
Right.
And one question from me is, I mean, in one of the slides and also in your paper, you showed these total cycle counts, and you did kind of break down into like convolution cycles and depth-wise. I mean, but did you, yeah. But let's say for some of the ones that, let's say, the convolutions are dominating, or like the depth cycles are dominating, did you kind of look further into if some specific layers are dominating, or what kind of causes this domination from one or the other?
I looked into it. I'm not sure if I've prepared slides into the individual layer breakup. No, it doesn't look like it. But depending on so we've tested different parallelization strategies indicated by the last letter, so input or output parallel, and the dominating layer depended also on the strategy. So for the input parallel, it was usually the first or the initial convolutional layers due to low hardware utilization in these layers.
Okay. So any other questions from the audience? So then, yeah, let's conclude this paper. Thank you very much, Max, for your presentation again.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotg, and Synsense.